Hey kids. Oh my goodness, look at all that homework. Right? That looks like a devastating list. It's not really, I promise. Half of them are going to go really quickly. They're just practice with some pretty rote calculations. So you'll be okay with that. And then the second half are some applications. Speaking of applications, this warm up is an application of some vector operations that you already know how to do, which is add vectors and to deal with vectors given to you like this, with when you have the force in pounds and the angle in degrees. So maybe you want to pause the video and do this on your own. But the work I would be looking for here would be for you to show me that you are adding these three vectors together. And when you add these three together, this is a free body diagram. This is the word I couldn't remember before physics diagrams. Free body meaning nothing is holding this down. And then you've got, think about these three people like kind of playing a tug of war with it. Where would it go? Given that force and the angle of each one, where do you think you would end up when you've got a force going from the, first quadrant, second quadrant, and a little fourth quadrant, almost directly, south? What do you think would happen? And maybe and hopefully then when you get your resultant vector, you're not surprised. So remember, you're adding each of the horizontal and vertical components. Horizontal is cosine, vertical is sine. And we did the triangle trig, right? When we kind of like did the force that went along with each one of these. This one is at 98 pounds right here. So when we added all these up, I'm not going to copy it all over, just tell you I got 47.3 and 51.3. And maybe that doesn't surprise you. Where would that be? Quadrant 1, right? And at 47-ish and 57 something, a little bit more than a 45-degree angle right through here in quadrant 1. So that is the resultant. What's the magnitude? Right? Magnitude would be the square root of the sum of the squares. Now, when you're on an assessment, follow the rounding rules of the assessment, right? I'm just on a warm up here. I felt like rounding to the 10th, so I did. I got 69.8. pounds. And what else do I need? I need a direction, right? How do I get the direction? I mean, there's a variety of ways. These are all triangles, right? There's a variety of ways I can get it. Since I have a y component, a sine, and a cosine, I will do inverse tangent of the y over the x. I expect a positive angle, and the calculator is going to give me a positive angle since my ratio is positive. And I'm in quadrant 1, so I don't have to do any manipulating. And I got 47.4 degrees, which is a little bit more than 45 degrees, right? Measuring from the horizontal. Good, right? So what we're going to do today is another vector operation called the dot product. So you should think multiply, because that's what product means. This is a vector operation. And what you get out of the dot product is a scalar, right? Or a number is what you get out of the dot product. So you are operating on vectors and you're not getting another vector. You're getting a number, a scalar. So I want to teach you to calculate the dot product, and then we're going to use the dot product. All right? There, I've taught you how to do the dot product. Done and done. The dot product, represented with a dot between two vectors, is the sum of two products. Product of the horizontal, product of the vertical components between two. And as I told you, I teased this in the prior video, the dot product gives you a number that talks to you about the parallelness. Yes, I made up that word, of two vectors. Right? So how parallel? So, and reducing that to just a number. So I think the easiest thing to tell you is, what number do you think represents two vectors that are not parallel at all? In other words, they're perpendicular. They have no parallel component to them. That dot product is zero, zero parallelness. So vector A and vector B are parallel. Their dot product is equal to zero. Whoops. If vector A and vector B have an angle that is acute, the dot product is positive. If theta is obtuse, the dot product is negative. All right. So let's practice. Oh no, so first I want to give you a couple properties. A lot of the properties of multiplication in real numbers holds with the dot product with vectors. The dot product is commutative. I'm going to skip number 2 for a minute. I take any vector and multiply it times a zero vector. I am going to get a zero vector. You can kind of sort of think of the distributive property here with vectors. And then also with this other constant or scalar, it doesn't matter if you multiply the scalar times one vector and then do the dot product, or multiply the scalar times the second vector and then do the dot product, or do the dot product first and then multiply by the scalar. Those are all the same. 2 says if you have a vector u, let's pretend that's, I don't know, 4, 2, maybe. How parallel is it with itself? Well, it's pretty freaking parallel to itself, right? What happens when you do the dot product with itself, though? If you follow these rules, right? What is 4, 2 dotted with 4, 2? Well, I get 4 squared plus 2 squared, don't I? But what is that? That is the magnitude squared, right? Because the magnitude is the square root of the sum of the squares. That's the magnitude squared. Oh, that's kind of cool. Again, though, notice that you're not like getting 1, right? You're getting you're getting a number, and then when the number of the dot product is not 0, again, I can tell whether it's positive or not. I can tell acute or not, or obtuse, versus whether the dot product is positive or negative. But really, that number, when it's not 0, I need it to compare maybe two vectors. Oh, these two vector, one pair is more, is closer to being perpendicular or closer to being parallel than the other. So for instance, when I just ask you to evaluate this dot product, again, you are just doing the product of the horizontal and the product of the vertical. What does that number 20 mean? Right? I don't know. It's a positive number, so there's an acute angle between them. So let's pretend that, again, there's one vector. Let's pretend that one is 7, 2. And 2, 3 looks like this, maybe. Right? You can see that the angle between them is an acute angle, right? What that 20 represents, don't worry so much about what 20 means, as opposed to if I give you this second pair of vectors. Now, I and J, it's kind of a little weird to have I and J like this. Don't really see that often. I just want to make clear that you know when you're doing a dot product, I'm going to get a number out of this, right? Not a vector. So 3, 6, where is that? 3, 6 here, maybe? And 1, 4. Whoa, look at those. My scale's kind of bad. But look at the angle between those two compared to the blue. So what do you think the dot product is going to be relative to 20? It's still going to be positive, but do you see how it is 3 plus 24? It is a bigger number than 20, meaning more parallel than the first pair. Hey, what if I had a negative here? What would my dot product now be? My dot product would be 3, but it would be minus 24, wouldn't it? Negative 21. What does that mean? My dot product being negative. Let's draw. So 3, negative 6. Maybe looks like this. And 1, 4 looks like that, right? That angle is obtuse. Dot product, negative. All right, speaking of the angle between the two vectors, let's think about trying to find the angle between them. So there's the angle I'm after. What if I called this vector u and this vector v? That vector, can you see that that vector would be v minus u? Does that make sense? Right, if you think about, right, and if it doesn't make sense, just like, oh, let's see, what if u was 4 comma 5 and v was 1 comma 6? What is v minus u? And then think about, right, you get this vector right here. Right, and remember, you can click and drag vectors wherever you want. But notice what I have now is a triangle. So I'm going to give you the formula for the angle between the two vectors, right? That's the same formula. One, I just isolated theta and got inverse cosine by itself. Notice that it is a ratio of a dot product to the product of magnitudes. But if we think about where this came from, remember again, think about this as a triangle, and you want one of the angles of the triangle. Law of cosines. Sound familiar to anyone? Gosh, it feels like last year. It was last year. I mean, it was last semester, but it was still 2020, right? When we did the law of cosines. Right? Law of cosines is, here's the angle. The side opposite it is, right? We used to think of that as like a squared equals the sum of the other two minus 2 times the product of the other two times the cosine of the angle opposite this side. Well, what are our names? Right? The length of this blue vector is right there. The length of the other two sides, the adjacent sides, here, minus 2 times the product of the adjacent sides times the cosine of the angle opposite the side that's on the other side of the equation. Now I'm going to drop those magnitude bars for a second while I do algebra. Something squared is write it down twice and multiply. I didn't touch the right side of the equation. There's me just distributing, right? But remember what I said with v dot v and u dot v? What does that equal from the slide before? And now look, by. Oh, my Lanta. Divide through by -2. Bye-bye. Isolate cosine theta. That formula just came from the law of cosines. Oh, snap. Pretty cool. This is the formula to use. I mean, you don't have to memorize a whole new formula, really. You just need this. Or this one, right? Doesn't matter. Those are both the same. But in the red, if somebody asks you for the angle, you've already got the angle by itself. But sometimes you're going to be asked for the dot product given the angle. Okay, so there's two formulas. Which one would you use here? Find the angle. Use the red between this vector. And again, I don't like this notation per se. I like this better, but nobody cares what I like better. I have to know all the notation. So find the angle. So when I look at these, I think, oh, 4, 5, with 4, 5 maybe is here. And 3, -1 is here. So find the angle between them. Ratio of the dot product. 4 times 3 is 12. 5 times -1 is -5. Over the square root of what? 16 plus 25 times the square root of 10. So that's 7 on the numerator. 7 square root of, I wrote that down somewhere. I think it's 410. Oh, I forgot to write inverse cosine, didn't I? So do inverse cosine of that on your calculator. And I didn't plan this. I got the same when I rounded it. I got the same number that I got in the warm-up, except the 69.8 was a magnitude in the warm-up. And here is an angle between. Does it make sense with my drawing? These right? I got a dot product that was positive, so I expected my angle to be less than 90. It was kind of small, kind of close to 0, meaning, right, close to, what did I say? An acute angle because it was positive. And it was kind of close to 0, so I have an angle, 70 degrees, fairly close to being, right, a right angle. How about this problem? Which formula would you use? Find the dot product. So you might want to use this formula. So here, find the dot product. The dot product u dot v, which I know how to get if I had the two vectors, but I don't have the two vectors. I know how to compute the dot product if you give me the components. Notice I wasn't given the components here. So I can find the dot product because somebody gave me the magnitude, right? So I have u times v, 12 times 3 is usually 36, times the cosine of 118 degrees. Now, when I get this answer, I get almost negative 17 degrees. I'm sorry, just negative 16.90. What does that mean? Oh, well, duh, right? I already knew that. I have an obtuse angle, so my dot product should be negative. My dot product should be negative. Orthogonal. I feel like I have to have tea and raise my pinky when I say orthogonal. It is just a fancy word for perpendicular. Orthogonal and parallel vectors. We've talked about this, right? Two vectors are perpendicular if and only if their dot product is 0, meaning they have not one iota of parallelness about them. 0 parallelness means orthogonal or perpendicular. However, parallel is not quite the same in our usual like algebraic XY plane, right? Parallel in algebra 1, same slope, different y-intercept. Coinciding lines, same slope, same y-intercept. In vector land, those are the same. Whether if you think of two lines who have a same slope, all that's required to be parallel is basically the same slope, which means you can just be a scalar multiple of one another, right? So for example, let's do 7, 3. There's 7, 3. Negative 6, 14. And 3, negative 7. Now look at how I've drawn these. Can you see the parallelness? Parallel in vector land, and can you see the perpendicularness? Right? Anytime an IB test says show that, or an AP test says show that, it means there's not going to be any points for the result of your calculations. It's going to be the setup and interpretation of your calculation, because after all, they're telling you what the answer is. So let's do parallel first. Parallel really has nothing to do with the dot product. Parallel just means scalar multiples of one another. So if they are talking about B and C, look at B and C there. All you have to do to show parallel, you say parallel vectors are scalar multiples. And B is a scalar multiple of C. And just tell me what that scalar multiple is. Can you see what it is? What can you multiply both the horizontal and vertical component of, and you could do it to either vector, right? I hope you can see that that's 2, but you could have put 1/2 here, and right? It doesn't matter. As long as you can multiply one vector by a scalar and generate the second vector, you have shown parallel. Let's do orthogonal though. So orthogonal, so check, I've done that one. They want me to show that A is orthogonal to both. So they want me to show that vector A dotted with vector B equals 0. And they want me to show that vector A dotted with vector C is equal to 0. Check. Check. Therefore perpendicular. Okay. And even though my drawing is pretty pathetic, I think you can see that A is orthogonal to B, A is orthogonal to C, B and C are in vector land parallel, scalar multiples of one another. And remember, in vector land, we can click and drag C, keep it same length and direction, but place it anywhere, and then it would look like a line with a different y-intercept, right? All right, projection. Projection is kind of weird, so hang with me here. What the projection of vectors allows us to, the projection of the vector is just a vector. Remember, the dot product is a number. The projection of a vector is a vector. What we use the projection of vectors for is to break up a given vector, break up one vector into its perpendicular components. Where A and B are orthogonal, okay? So projection, I want you to think of a spotlight. So here is vector U and V, and I want you to picture right? Some kind of light bulb, some kind of spotlight here, shining. You're shining down onto vector u. Its shadow or projection down onto vector v is another vector. The projection is a vector. It's the green vector. Do you see, though, that the projection vector of u, and this is how it's written, projection of u onto v, is just a scalar multiple of vector v. Do you see that? Just a skip, right? Because you're getting the shadow down onto vector v, but then the shadow lies on v, so it is just a scalar multiple. In my drawing, a shorter one of v, right? So you would need to scale v down to get, right? The scalar would have to be a number smaller than 1. So what's in these parentheses is just a number. This is your scalar, right? The dot product, right? And the dot product is a number. The magnitude is a number, and the magnitude gets squared. So that green vector is called the projection of u. Now, let's practice a little bit. Find the projection of 2, 5. Let's pretend u is 2, 5, and v is 7, 2. Find the projection of u onto v. So if it's onto v, the shadow of u goes onto v, so drop the v down here. So the projection of u onto v is a scalar times v. And that scalar is the dot product of the two given vectors. So 2 times 7, which is 14, plus 5 times 2, which is 10, over the magnitude of v. Squared. What happens when you square that? So my scalar is 24 over, what is that, 53? And I think I will just leave it like this for now. I don't have to multiply that in. That's the projection of u onto v. Now, that takes care of finding a projection. But I want to use that to break a given vector, and I'm going to pick u because I projected u onto v. I want to break u into a sum of two vectors, vector A and vector B, where A and B are orthogonal to one another. So write u as a sum of two perpendicular vectors. Oh, one of the vectors that I want is the projection of v onto u. Oh, all right, all right. So what you're saying up here is I want to write u as a addition of two vectors, one of which is the projection of u onto v, and the other one is a vector perpendicular to that. Can you visualize where that's going to be? It's going to be right here, right? How do I know what that is? Well, let's do a little tip to tail addition subtraction stuff. What is that green vector? Isn't that just the negative of projection v? Oh, look at that, my negative was floating way up there. That's just the opposite of the projection of u onto v, right? And then click and dragged up here. Why would I want to do that? What's that? That's u minus, right? To complete that triangle, u minus the projection of u onto v is this purple. And look at that purple vector. That purple vector goes from the origin and is going to become B. So breaking up U as a sum of its perpendicular vectors, one of which was the projection of U onto V. So we've already done this. So we're going to write U is equal to 25 over 53 times 7 comma 2 plus U minus that value. That vector, I should say. So I used my calculator and I did some math. And I got, what are the numbers that I got for this? I wrote them down somewhere. Oh, here they are. Negative 62 over 53 and 217 over 63. I'm sorry, 53. And whatever 25 times 7 is, what is that? 175 over 53 plus 50, whoops, sorry, comma, 50 over 53. That is, you add those two together. If you add the projection of V, I'm sorry, projection of U onto V plus U minus the projection, add those two together and you will get vector U. For reasons that you don't know, but I'm telling you, in higher level physics and in multivariable, there are lots, in 3 dimensions, lots of times where we need these two perpendicular components. Now, just think about, right, what you've done, really. I mean, every time you have a vector in, right, regular, like when I just have this vector here, right, you are breaking it, right? It's the horizontal, the horizontal 4 and the vertical 5, right? This vector is its horizontal and vertical component, right? And those two vectors, if you want to think about these horizontal and vertical vectors, they are orthogonal to one another. That's what you've just done here. It's just you weren't right? It's kind of like you made this V and its projection kind of sort of the x-axis almost, right? Kind of cool. All right, so that was the last thing that we needed to do. So the review, what did we do today or in this video? You learned what the dot product was and how to just calculate it. We talked about when you get a 0, when you get a positive, when you get a negative, what it means. We found how the dot product was involved in finding the angle between two vectors, which came from the law of cosines. We learned about, oh wait, I'm not done. I'm sorry. Oops, sorry kids. Oops, forgot there was one more thing to do. The dot product is involved in work. Work is a scalar. So we have done the dot product, what it is. We have learned about the angle between two. We have learned about the projection. of vectors, and we have learned how to write a vector as a sum of orthogonal vectors where one is the projection. And now we're going to talk about work. Work is a scalar quantity of energy, and it is computed as a dot product. Work is a dot product. Force dotted with direction. And the dot product is a product of the magnitudes times the cosine of the angle between them. That's the work formula. So here's Isaac. In the warm-up, I gave you a force of pounds, right? This in pounds. This unit is newtons. And I want you to find the work done by a 15 Newton force acting in this direction, moving an object 4 meters in the 4-1 direction. So what do I have here? So over here on my drawing, can you see which one is 2-3 and which one is 4-1? And I'm going to put the magnitude on the first one. I don't think so, Ms. Getz. 15 is not the magnitude, right? What's the magnitude? The magnitude of 2-3 is the square root of 13. That ain't 15. What the heck? And here's my 4-1 vector with a magnitude, right, in meter, just its unit is meters, of 4. I don't think so, right? The magnitude of this vector is the square root of 17, not 4. What the heck? So I'm supposed to do a dot product of force times direction, which is equal to their magnitude. No. What the heck? I need to be in the 2-3 direction, but I need a magnitude of 15 in order to actually do these operations. Any clue? Any clue? Because again, I got a big nope down here. This 4, it is not the magnitude of the vector 4-1, but I really want the magnitude to be 4. And I really of the second vector, and I really want the magnitude to be 15 of the first vector. Unit vectors. Unit vectors, right? So find the unit vector for F. How do you do that? Do you remember? You take the vector 2-3 and divide it by its magnitude. Find the unit vector for D, and that is 4-1 over the square root of 17. What is the length of both of these? 1. That's the whole reason for making a unit vector. What do I want the magnitude to be? 15. See what you want and legally make it happen. Whoa. So what do I get over there? Here, I get 30, 45, both of them over the square root of 13. And here I get 16 over the square root of 17 and 4 over the square root of 17. Done and done. Now calculate the work. Find the dot product of F dot with D. And I get 30, 45, 16, and 4. And I think I'll just keep the magnitude out here. And I got 660 times 660 over the square root of 221, I believe. What does that? I did that, get a number on my calculator, and I got 444.4 joules. So joules is a unit, right? Because you had units on all of these, right? This was newtons and this was meters. You were multiplying them together. So a newton times a meter is a joule. Isn't that crazy? Named after a guy, right? This guy, oh, I forget his first name was, I liked his first name, but I forget what it is now. But remember, a newton is a kilogram, right? The force it takes to move 1 kilogram, 1 meter per second squared. And then you're doing a dot product with a meter. So this is a newton. Newton times a meter is kilogram meter squared per second squared. That we call a joule. And it's not joule like a ring on your finger. It's Joule. I'm so mad I forgot his first name. He's got 2 names. He goes by 3. It's something something Joule. I have his picture though. There he is. Look at that beard. Look at that beard. Right? So I guess the difference between Newton with his wig and Joule with his beard. Now I'm done. Now I'm done. Now notice I did find, right? I did the dot product to find work. I could have taken the magnitudes and found the angle between them, and I would get the same thing. All right. Have fun with that homework, and I will see you after break. Now I'm really done.